Hello, Matthews Gatos here. In this video, we are going to cover differentiable functions. So let's get started. What is a differentiable function? Well, a function is considered to be differentiable at some sort of point if the derivative exists at those points. So first of all, if a point is not in the domain of f of x, then automatically it's not in the domain of f prime of x. If f of x is differentiable at a point, then it has to be continuous. So differentiability guarantees continuity. Unfortunately, the other way around is not true. Continuity does not guarantee differentiability. But important to note, if a function is not continuous, right away we can say that it is not differentiable at that point. Okay, so let's look at 4 situations where the derivative fails to exist. So the first place is called a corner. So right here is a corner. So a corner is where piecewise functions come together. Now the reason that the derivative fails to exist is because the tangents, remember that's what derivatives are, slope of a tangent. So the tangents approach different slopes on either side. So the slope on this side I can see without even knowing the number. All of the slopes on this side are negative, whereas all the slopes on this side are positive. So that's the first place. Now, is this continuous at this point? Yes, it is continuous. The limit on both sides is equal to the function value, but not differentiable. So see, continuity does not guarantee differentiability. Let's look at this one over here, a cusp. So right here is a cusp. So the slopes approach different infinities on both sides. So it's almost like they come in to be a vertical line with an undefined slope, but from different perspectives. So on this side here, you can see that all of my slopes are positive. As it comes in, it's going to come into a positive vertical tangent. All of these slopes are going to approach a positive infinity on this side. But on this side here, you can see that they're negative and they're coming in and they're going to become more and more steep to like almost a vertical steepness. But on this side, they're approaching a negative infinity. Now, at that point, is the function continuous? Yes, it is. Left-hand limit equals right-hand limit equals the function value, but not differentiable. Okay, the third place that the derivative fails to exist is at a vertical tangent, okay? So I can see that on both sides here, these are approaching the same infinity on either side. They're coming in like this, getting steeper and steeper to like a vertical line. Same thing as they go here, they're coming into this vertical tangent line. So they're approaching the same infinity on either side. So is it continuous at that point there? Yes, it is, but not differentiable. Okay, the last type of place where a derivative fails to exist is discontinuity. So in other words, if a function is not continuous at a point, right away it is not differentiable either. So each one of these are examples of graphs that are not continuous. We learned this in our last chapter. Let's review this. Why this is not continuous is because I have a jump, a break in the graph. This is a jump discontinuity. Over here, I have a hole in the graph, but the function exists there. This is an example of a removable discontinuity. Over here, the function does not exist here because there is a vertical tangent, a vertical asymptote, sorry. So these are not continuous because they are considered infinite discontinuities. And then over here, the last one, this is not continuous at this point here because it is an endpoint. So there is no limit on the other side. So right away, if it's not continuous, I know right away it is not differentiable. So those are the different places where derivatives fail to exist. Let's look at an example. So here, what is f prime of x as x approaches 1 from the left? So here's where x is equal to 1, and you can see it's a linear function here. So as I get closer to 1, what is the slope? I can just pick 2 points here, and I can see the slope is going down 1 and over 1. So as it approaches 1 from the left, the derivative, which is the slope of the tangent line on that side, is -1. On this side here, let's look at the slope here. So this time I'm going up and over. You always go to the right, so down and to the right here. This one's going up and to the right here. So the derivative on that side is positive 1. So is it continuous at 1? Well, yes, it is. We can say that the limit as x approaches 1 of f of x is equal to the value of function at 1, because you can see in both of those cases it's equal to 0. So yes, it's continuous, but it is not differentiable, okay, because you can see that the slopes are different on either side. Okay, let's look at another example. So at -2, so -2 right here, okay, what happens as I approach -2 from the left-hand side? So from the left-hand side, you can see I'm going up to, it's getting steeper and steeper and steeper and steeper. It's approaching a positive infinity. Okay, on the right-hand side, I can see that all of my slopes on this side here are negative. So it is approaching an infinity, but remember, we're talking in terms of the slopes. It is approaching a negative infinity. So is it continuous at -2? No, because we have a vertical asymptote there, so an infinite discontinuity. So if it's not continuous, right away I know it is not differentiable. Okay, so let's look at this graph here, and I want to identify all the values of x where the following graphs are not differentiable. So very first place that I notice here is at -3. I have a vertical asymptote, so it's not continuous, therefore not differentiable. And it's not continuous because, let's look at my reasons here, I have an infinite discontinuity. Okay, I also know that the function is not differentiable at 1. Why? Because it's not continuous at 1, and if it's not continuous, it's not differentiable. And let's look at the reason there. I have a jump discontinuity. Okay, so jump discontinuity, not continuous, therefore not differentiable. And then the other place where I see it's not differentiable is right here at 3, and I can see I have a linear function on one side and a curve on the other. So this is where two piecewise functions meet. So it is continuous, but it is not differentiable because I have a corner. Okay, one last example here. So where are we not differentiable? I see right here at -2, we are not differentiable because I'm not continuous there. Okay, I'm not continuous there because I have a removable discontinuity. Where else do I see? Down here, I see it's continuous, but it is not differentiable because I have a cusp here. Okay, so the slopes are approaching different infinities on both sides there. And then the last place that I see that it is not differentiable is right here at 4. Now it's continuous at 4, but I can see that it's approaching here a vertical tangent, and that's why it is not differentiable. Okay, so those are all of my examples for differentiability. There we go. This reminds me, in calculus, I actually failed my calculus exam because I was seated in the middle of identical twins. Well, why do you think that would cause me to fail? Well, quite simply, I just couldn't differentiate between them. So I hope that this video helped. If it did, give it a thumbs up and hit subscribe so I can help more mathies just like you. Thanks for watching, and I'll see you for the next one.